Hello, everyone. Today is going to be a long lecture on the periodic table. Part 1, Part 2, and Part 3 will be done together. So have patience to complete this video series. Do remember to subscribe to my channel for more updated videos on chemistry. Now, I'm going to start with what is the periodic table, the introduction, and what are the periodicity in this topic. All right, so what is periodic table? It's the arrangement of elements in increasing order of proton number, such that elements with similar chemical and physical properties are grouped together. So it's actually a very organized way to organize the elements that are similar in physical and chemical properties. The horizontal rows are periods. So elements in the same period will have the same number of electronic shells. Vertical columns are called groups. So elements in the same group have the same outer electron configuration. Periodicity is a term that you should be familiar with. It refers to the recurrence of similar properties at regular intervals where elements are arranged in increasing atomic number. Now, we are going to learn about S block, D block, P block, and F block today. So you need to have prior knowledge of atomic structure to understand this part very well. S block refers to electronic configuration of valence shell NS1 and NS2. So they consist of metallic elements from group 1 and group 2. Okay, group 1 are called alkaline metal, group 2 are called alkaline earth metals, as well as the non-metal hydrogen is considered part of S block. The groups 1 and group 2 metals, they have relatively low density, melting point and boiling point compared to other metals. They are reactive and are high in the electrochemical series. So they will have low first IE or low second IE. The metals form stable, non-volatile ionic compounds with non-metals. So these are the characteristics of group 1 and group 2 metals, as well as in the S block. Okay, focusing more on the metals. As for the P block on the other side of the periodic table, they are the one with NS2, MP1, all the way to MP6. Their electronic configuration of helium, in this case, will be 1s2. So that's an exceptional case. So for P block elements, they consist of elements from group 13 to group 18. In general, they have low density, low melting point, boiling point. Exceptional case will be diamond, as well as graphite. In general, they form ionic compounds with metals and molecular compounds. It could be either macromolecule or simple molecules with the non-metals. The noble gases in this block are inert, but do note that at extreme conditions, noble gas do react. For D block element, they are the transition metals, all the way from 3D14S2 to 3D10-4S2. All right, so they are of the higher density, higher melting point and boiling point compared to the S block metals. They are definitely less reactive, which means they have higher IE actually. So across elements of the same period, the IE will increase. They form complex that are colored. Okay, they form color compounds, but they themselves are not colored as elements. So most of the metals are still gray metals, just like the group 1 and group 2 metals. Okay, the F block are no need to be so familiar with it. Okay, it's not tested much in the syllabus. Will be lanthanoids and anthanoids. They start from the 6th period. Now, what is the variation in atomic properties? So for atomic radius, okay, across a period, all right, the number of shells will remain the same. So across the period, the number of shells will remain the same. The number of protons increases, so nuclear charge increases, all right? Since the number of electrons increases, but the thing is the electrons, right, are added to the same outermost shell. So the shielding effect by the inner electrons remain almost constant. We know that effective nuclear charge equals to nuclear charge minus shielding effect. So with increased nuclear charge as almost constant shielding effect, effective nuclear charge increases, which explain why the electrostatic attraction between the nucleus and the valence electrons increases and decreases the size of the electron cloud, where the valence electrons are brought closer to the nucleus. That results in a decrease of atomic radii across the period. Okay, so this explains the trend of atomic radius across the period. So in general, it is decreasing due to increased effective nuclear charge. For ionic radius, we have to bear in mind the difference between the cations and the anions. For the cation, their radius will be always smaller than the parent atom. That is because both cation and parent atom do have the same number of protons, but because the cation have less electrons, okay, and less electronic shell. So normally the cation will have one less electronic shell, but the number of protons remain the same. So the nuclear charge remain constant. So same nuclear charge, but one less electronic shell. The effective nuclear charge, okay, is actually increases, okay, because now you have less shielding effect, but nuclear charge remain the same. So effective nuclear charge increases, okay. So that will result in the increased electrostatic attraction between the nucleus and the valence electron, and hence the size of the electron cloud decreases as the electrons are brought closer to the nucleus. That is for cations. For anion, the radius of the anion will be always greater than that of the parent atom. Both the anion and the parent atom have the same number of protons and have the same nuclear charge. However, the anion has more electrons than the parent atom. So with more electrons, we expect more electron repulsion. Okay, with more electron repulsion due to the added electrons, electrostatic attraction between the nucleus and the valence electrons decreases, okay, which increase the size of the electron cloud. So you will see that the radius of the anion is greater than the parent atom. Isoelectronic ions refer to ions having the same number of electrons. So for these isoelectronic ions, the ionic radii will decrease across the period. For example, from sodium ion to silicon, number of protons and nuclear charge increases. Shielding effect, same. Effective nuclear charge increases. All right. Electrostatic attraction between nucleus and valence electrons increases. That decreases the size of electron cloud. This same reasoning will be extended to include ions that are isoelectronic to sodium to explain the decreased ionic radii from carbide to silicon. Similar for phosphide to calcium. All right, same reasoning. Now, if you look at the first IE, the trend has been discussed in the topic of atomic structure. So I will just quickly run through as a form of revision. First IE of elements in general increases across a period. Okay, same reasoning as above, with the number of shells remaining the same, the number of protons increases and increases the nuclear charge. Number of electrons may increase, but the electrons were added to the same outermost shell. So the shielding effect by the inner electrons remain almost constant. This results in an increase of effective nuclear charge. Hence, the electrostatic attraction between the nucleus and the valence electron increases, resulting in an increase in the amount of energy to remove the valence electron from the atom. So in general, the first IE of elements increases. However, there are some irregular characteristics to be observed. For example, in between magnesium and aluminium, between group 2 and group 13, the discrepancy is that instead of having the first IE of aluminum greater than magnesium, we have it even lower. That is because the 3p electron to be removed from aluminum was actually at a higher energy level than the 3s electron from magnesium. So aluminum 3p electron is of a higher energy level. So that requires less energy to remove the 3p electron. All right. So the first IE of aluminum is lower due to a higher energy level of the 3p electrons. Another irregular characteristics between group 15 and group 16. So the 3p electron to be removed from S is a paired electron, while that to be removed from P is an unpaired electron. So there are inter-electronic repulsion between the paired electron in the same orbital in sulfur, so that requires less energy to remove the paired electrons. So because there's repulsion, so we take less energy to remove. So the first IE of sulfur is lower than P. As for electronegativity, the number of shells remain the same across the period. So we have increased number of protons, and hence nuclear charge increases. So the number of electrons will increase, but these electrons are added to the same outermost shell, which causes the shielding effect to remain almost constant. All right. Effective nuclear charge increases across the period that was already discussed earlier. So the electrostatic attraction between the nucleus and electrons that are being bonded increases. So the electronegativity will increase. Electronegativity is defined as the extent of attraction of the nucleus on the bonding electron. So if the attraction to the bonding electron is stronger, that will result in increase in electronegativity. Now, let's look at the trend of melting point of sodium to aluminum across the period. Sodium, aluminum, magnesium, they are metallic structures, so we can also list them as giant metallic lattice. They have strong metallic bonds, electrostatic force of attraction that exists between the positive metal ions and the sea of delocalized electrons. So across the period, we do see that the strength of metallic bond increases from sodium to aluminum. Okay, there is an increasing number of delocalized valence electrons, as well as decreasing cationic size. So as we learn that charge density equals to charge over density, so with increased charge and decreased size, okay, so charge density is actually charge over volume, not density. Yeah, so it should be volume over here. Yeah. So with the decreased size, the volume decreases, so your density will increase. All right. The energy required to break the strong metallic bond will increase from sodium to aluminum because of the strength of metallic bond increases. All right. More electrons, stronger the bond. Decreased size, stronger the bond. Because the electrons are closer to the nucleus, we strengthen the metallic bond. For silicon, they have a giant molecular structure with extensive network of strong covalent bond between the silicon atoms in tetrahedral arrangement. So that means a lot of energy will be required to break the numerous silicon-silicon bonds. So the melting point is the highest among the period 3 elements as observed. It's a giant molecular structure, which explains why it has the highest melting point across the period. The rest of it will be phosphorus, sulfur, and chlorine. They are simple molecular structure with weak ID-ID interactions between molecules. The strength of ID-ID interactions depend on the number of electrons or the size of electron clouds. So as we know, chlorine, the molecular formula was actually Cl2. Phosphorus was not P2, it's P4. So sulfur is S8. So based on that, the electron cloud size of sulfur should be the greatest, which explains why it has the strongest ID-ID interaction, which means the most amount of energy to overcome the ID-ID interactions, hence the higher the melting point. With greater size of electron cloud, we can also say that electron cloud are more polarizable. Next, let's look at electrical conductivity. It refers to the material ability to conduct electric current. So for elements across period 3, the conductivity in general depends on the number and presence of mobile charge carriers. In this case, the delocalized valence electron for the metals. Okay, so sodium, magnesium, aluminium, they are metallic structures with strong metallic bonds between the positive metal ions and the C or delocalized electron. So it is good conductor of electricity because of the presence of delocalized electron to act as charge carriers. So the conductivity will increase from sodium to aluminium with increasing number of delocalized electrons. So with more electrons, more mobile charge carriers, the conductivity increases. As for silicon, it is a giant molecular structure with strong covalent bond as discussed earlier, but it is only, you see, it drops a lot because it's a meteoroid, meaning it is not really a very good conductor. Yeah, it only conducts at certain temperature. So just take note that, but silicon can be a good conductor at high temperature. So it is known as a semiconductor. This is the characteristics of semiconductor. From phosphorus to chlorine, right? They are simple molecular structure, non-conductor of electricity, electrical insulator due to the absence of mobile charge carriers. Unfortunately, they do not have mobile charge carriers. There's absence of delocalized electrons or mobile ions to add mobile charge carriers. Just to take note that although some materials, if they are poor conductor, it's not necessarily true that if the material is a good conductor of electricity, it will be a good conductor of heat. No, they are not the same. For example, diamond may be a poor electrical conductor, but it's a good thermal conductor. So do not, it may correspond to some materials like metals, but not other materials. Yeah. Trends and variations in chemical properties. So let's look at now just now we'll be looking at the physical properties. So we are now examining the chemical properties of the elements. So what will be their reactions with oxygen, chlorine, and water be like? So let's start with, maybe we just look down the trend. Let's say we focus on oxygen first. All right, so why this need to be dry is because we do not want the element itself to react with water, as the elements are capable of doing so. All right, so we just want the element to react with the oxygen and chlorine gas and not water. So the condition has to be dry, anhydrous in a way. All right, no water present to prevent reaction of the metal with the water. So sodium with oxygen, it forms sodium oxide. That's quite obvious. And because sodium is a very reactive metal, the reaction will be very vigorous. Okay. Likewise, magnesium, although it's not as reactive as sodium, it will still be a vigorous reaction with oxygen, but definitely less reactive. And now, if we look at aluminium, the reaction of aluminium oxygen also produced metal oxide, aluminium oxide. It was actually a vigorous reaction, but not very vigorous. However, the oxide layer that was formed will quickly stop further reaction. Okay? So it will be vigorous at the start, then it stops. Silicon reacts with oxygen to form silicon dioxide. That happened, but very slow. Then we have a change. Phosphorus itself is considered quite reactive, unstable, so it will react readily with oxygen. So the reaction of phosphorus with oxygen will be vigorous to form P4O10, phosphorus oxide. Phosphorus 5 oxide. Yeah. For sulfur, it will first react with sulfur, oxygen to form sulfur dioxide, and it will undergo further reaction with oxygen further oxidized to form sulfur trioxide. So the reaction is considered slow. Yeah. And SO2 can be further oxidized under controlled conditions like a catalyst. Like catalyst could be the vanadium oxide. Okay, a transition metal oxide could be used. So slow, vigorous, yeah. So look at the trend here. So it will like the reaction rate will drop among the metals across the period, and then silicon slow, and then phosphorus vigorous, then drop again. Then for chlorine, no reaction with oxygen. No. How about with dry chlorine and heat? So sodium with chlorine reaction is very vigorous. But when you talk about magnesium and chlorine, it is just vigorous. All right. Aluminum and chlorine form aluminum chloride. So this reaction is still considered vigorous, and it's often done by passing the dry chlorine over aluminum foil heated in a long tube. All right. Very pure yellow aluminum chloride is formed, but then because it's a simple molecular structure, it will sublime and then collect further down the tube when it's fuller. So just take note that aluminum chloride is actually a simple molecular structure, not ionic structure. Okay, silicon with chlorine forms silicon tetrachloride. This reaction is slow, and phosphorus, as we know, it is reactive, unstable element. It will react vigorously with your chlorine to form phosphorus 5-chloride. Yeah. Then this is not in the syllabus, just for information. Then for water, this is what we learned in O-level. Sodium reacts with water, form an alkaline, sodium hydroxide and hydrogen gas, very vigorous. Magnesium with water, very, very slow. In fact, it was mentioned that it takes a few days for reaction to be completed. It does form magnesium hydroxide, but magnesium hydroxide is actually insoluble in water. Then we have magnesium and steam form magnesium oxide. This is covered in O-level under the topic of metals. Then aluminium does react with steam, but not with water. Okay, this reaction is vigorous at the start, but of course, due to the oxide layer, to prevent further reaction. Okay, the oxide layer form soon prevent further reaction. I think that will be better. Okay, then silicon, no reaction. Phosphorus, no reaction with water. Sulfur, no reaction with water. But chlorine does react with water. This is called disproportionation reaction. It's a type of redox reaction where the same substance is reduced and oxidized at the same time to form two different products. So when chlorine reacts with water, it forms an acidic solution. HCl is a strong acid, but HOCl is a weak acid. All right. Very little amount, because you see this is a reversible reaction. So the extent of dissociation is low. Okay, it's a weak acid. So very low amount of HCl and HOCl are formed. So the pH is not very low and only slightly below pH 7. So some people ask, is it very acidic to put chlorine in swimming pool? Don't worry, it's very mild. Now, the maximum attainable oxidation number are periodic. So the oxidation number exhibited by the element will correspond to the number of valence electrons gained or lost by the atom of element to achieve electronic configuration of Ns2np6 in the formation of ionic compounds, or the number of electrons shared by atom of element in the formation of covalent bonds. So if we look at these elements, so the oxide of the highest oxidation state will be here +1, magnesium +2, aluminum +3, silicon +4, and phosphorus can go all the way to +5, and sulfur all the way to +6 actually. Yeah, can. So the valence electrons correspond to the maximum oxidation number that the element has. So for the chloride form, we have sodium chloride, magnesium chloride, aluminum chloride, silicon tetrachloride, phosphorus chloride, okay? And this is not needed in the syllabus. Okay, so we can see that the maximum oxidation number and the number of valence electron correspond to each other. All right, not to worry. So moving from left to right across the third period, the oxidation number of each element in its respective oxide and chloride is always a positive integer because both oxygen and chlorine are more electronegative than each of them. Okay, so you can see that oxygen and chlorine are more electronegative. So the element, right, will always be a positive integer. Yeah. So you can see all the positive. The maximum attainable oxidation number of each element will correspond to the number of valence electrons in each atom of the element. So that is all the valence electron can be used for bonding. Okay, that will be the maximum number of valence that the valence electron will correspond to the maximum oxidation number. This is because for period 3 elements, these are all period 3, they do have unoccupied low-lying 3D orbitals that can be used for bonding through the expansion of the octet structure, like PCl5, P4O, then SO3. So they can hold more than 8. They don't really obey the octet rule. They can go beyond that to hold more than 8 electrons in the valence shell, because they do have 3D orbital that can form bonds. Now, in general, with a large difference in electronegativity will give rise to ionic bond. Small or no difference will give rise to covalent bond. Across the period, both the oxides and chlorides by period 3 element will become less ionic and more covalent because of the decreasing difference in electronegativity difference. So if you look at the trend here, okay, let's examine the trend of the oxides first. So for sodium oxide to magnesium oxide to aluminum oxide, okay, of course, they are good electrical conductivity and increases across the period. Ionic, yes, it's still considered ionic, but you see that I'm going to explain why this is actually lower than this. So for these 3 oxides, right, since they're ionic compounds, we acknowledge the strong ionic bonds between the opposite charge ions. And the strength of ionic bonds is directly proportional to the lattice energy, which is directly proportional to the product of the charges of the 2 ions and inversely proportional to the sum of the radii, okay? The cation and the anion. As for the non-metal oxides, okay, electrical conductivity is no, okay, because axioms of mobile charge carriers. For silicon dioxide, very, very high melting point, but not as high as magnesium oxide, but still high lah. Is considered having strong covalent bonds, okay? As for this, because the thing is why you cannot, it's not like, not like graphite and diamond, because the thing is silicon oxygen bond, right, it's not so strong compared to carbon actually. Yeah. Then for this one, simple molecular has to do with the ID-ID interactions. So if you have more electrons, you have greater size of electron cloud, more polarizable, your strength of ID-ID interaction should increase. So why this is so special is because it could be, there are 2 reasons why aluminum oxide has a lower melting point compared to magnesium oxide. So it could be the difference in the packing. So the packing may not be so efficient and good in aluminum oxide. That result in lower melting point. So you can actually justify with poorer packing in aluminum oxide than magnesium. Okay, so that's one way to justify. Then another reason is aluminum oxide is not entirely ionic. There are some slight covalent character due to the high charge density of aluminum ions. So with a high charge density, the polarizing power is strong. It's able to polarize, you see, the chloride and form covalent bond instead of ionic bond. So there's some tendency of covalent bond between the aluminum and oxide. Yeah. Polarize Okay. Now this is the physical properties of the oxide. How about the reactions of oxide with water? What will it be like? Okay, so there are some things to study. Later we go to the chloride. So sodium oxide, magnesium oxide, aluminum oxide, we know they're ionic. And when they're added to water, so these are the observations. So for sodium oxides, right, and magnesium oxide, for sodium oxide, it will just dissolve to form sodium hydroxide. Okay, so when sodium oxide is added to water, it will form sodium hydroxide. It will form a strong alkaline sodium hydroxide. So the pH is between 13 to 14. For magnesium oxide, right, the problem is it's only slightly soluble. All right, so it will not be a complete reaction. I think it will be a reversible reaction, forming magnesium hydroxide with some of it dissolving. So it is just in equilibrium, you see, between, it's equilibrium between the solid magnesium hydroxide and the aqueous magnesium hydroxide. So for magnesium oxide, it does not really react so readily with water because magnesium oxide is only slightly soluble, because the lattice energy is highly negative, so very difficult to break the ionic lattice. Yeah, due to the high charge. Moving on to aluminum and silicon, right? They are definitely insoluble. So if you add to water, it will just be pH 7. Aluminum oxide does not dissolve in water because of the high charge and low radii. Okay, the lattice energy is highly negative, so impossible. The water molecules is unable to react with it. It's unable to break the ionic lattice because of highly negative lattice energy. As for silicon dioxide, it does not dissolve because of the strong SiO covalent bond. So the water molecules cannot form interactions with it. Okay. These two are simple molecular. They do react readily with water to form acidic solution. All right. So the pH, so this P4O10 reacts with water form phosphoric acid. We are all familiar with this. It's a weak acid. It dissociates partially in water. SO3 dissolves in water to form H2SO4. Okay, and this reaction is highly exothermic, which means a lot of energy release. So you will see acidic mist form. So this is the graph of the pH against the oxides of period 3. Now, for the ionic oxides, right, to react with water, they must be first able to dissolve. So the oxide ion release should be a very strong Bronsted-Lowry base. Okay, so being a Bronsted-Lowry base means that it will accept proton from water. All right. For the covalent oxide, right, the highly electronegative O atom will cause the other element to be highly electron deficient. Okay, so sulfur becomes partial positive. So it becomes susceptible to nucleophilic attack. So the water molecules is able to attack the positive sulfur to form your oxo acid. And from the oxo acid, right, another water molecule can carry out nucleophilic attack on one hydrogen to remove the H from here to form the HSO4 minus and H2O plus, make it acidic. HSO4 minus, yeah, correct. Now, let's look at the acid-base nature of the oxides. So for sodium and magnesium oxide, they are basic. So when they react with acid, it neutralizes it, undergoes neutralization. I shall not elaborate on this. Okay. For aluminum oxide, it's an ionic compound, but with some covalent character. So it's amphoteric. Okay, it's amphoteric. So it can react with acid as well as with alkaline to form sodium aluminate complex. Okay, now you have to learn this. Okay, complex. All right. For the hydroxide, yeah, same thing here. Just that for sodium hydroxide, right, it will act as a Lewis base acid, Lewis acid, by accepting the electron pair. Right, no, donating the electron pair, sorry. You know, accepting electron pair. Yeah, that's right. Na plus. Form sodium aluminate complex also. Yeah, same thing lah. As for these three acidic, they react with alkaline to form, yeah, a salt. Na2, SiO3, and so forth. Sodium sulfide. Okay. It should be sodium sulfate. If it's SO2, will form sodium sulfides. This is sodium sulfate. This is sodium phosphate. Okay. So that's for the oxides. Reaction of the oxides with water. Okay, reaction of oxides with acid or base. Now let's go to the chloride. Okay, so for chloride, we focus on sodium and magnesium chloride first. They are good conductor, ionic compound, giant ionic lattice structure. Okay, blah blah blah. Aluminum chloride, right, is actually a simple molecular structure. Okay, really more towards that. Then no mobile charge carrier present, and you use their, to explain their melting point, right, you have to use the weak ID-ID interactions lah. Yeah. So a possible reason to explain why magnesium chloride is slightly lower than sodium chloride is because of some slight covalent character. So we do understand that magnesium chloride has considered a high charge density because of the high polarizing power of magnesium 2+. So there's some covalent character, not a lot, but it's still considered ionic overall. All right. So in the solid state, aluminum chloride actually form a crystalline lattice of aluminum Al2Cl6 unit. In liquid and vapor state, it exists as dimer. The size of electron cloud explain the observed BP. So Al2Cl6, right, has the highest boiling point because of the greatest MR, greatest number of electron, greatest size of electron cloud. Okay, followed by PCl5 and lastly SiCl4. Okay, but take note, only at high temperature, the dimer will dissociate to form back the monomers of AlCl3. Okay, so this is the dimer. As for the reaction of a chloride with water, they do differ. We're going to talk about what is hydrolysis here. So there is a difference between hydration and hydrolysis. All right. Hydration means just, dissolving in water. Okay. It is reversible. But when you say hydrolysis, right, it's actually reaction with water. So it's very different. So when sodium chloride is added to water, the pH of resultant mixture will be 7. Because it's just hydration taking place, where sodium chloride dissociate to form sodium ions and chloride ions. That's it. That's hydration. Dissolving is hydration in a way. Dissolving brings about hydration, where hydration means the sodium ions or the chloride ions surrounded by water molecules. So it's called hydration, where the ions are surrounded by water molecules. For magnesium chloride, it's ionic with some covalent character. It dissolves readily with slight hydrolysis. So the pH is lower than 7. All right. So there is hydration, okay, where an aqua complex, okay, is formed. But once the aqua that is Okay, that is, but if there is, but the reaction doesn't stop here. So upon hydration, you form an aqua complex, all right, releasing the chloride from it. But that's not the end. So there's some extent of hydrolysis where this aqua complex, right, undergoes hydrolysis reaction with water. So what happened is that it breaks OH apart here and H releases. So the H3O plus is formed, acidic. So from 2 plus become 1 plus because 2 plus minus 1 here become overall 1 plus charge. So because of, then this is also reversible. So it's not a complete dissociation, it's a partial dissociation. Okay, forming the hydrolysis brings about H3O plus. So that explains why magnesium chloride, the pH is 6.5 . Yeah, that's the explanation. Yeah. So actually, there is some nucleophilic attack by the water on the H here. Yeah, there's nucleophilic attack by the water on the H. So it forms the H3O plus. As for aluminium chloride, which is a simple molecular structure, it dissolves readily with appreciable hydrolysis. So the pH actually dropped to 3. So there was a higher concentration of H3O plus, resulting in lower pH. So first of all, it undergoes hydration first to form an aqua complex again. So the aqua complex, right, will react with water. So this undergo nucleophilic attack again. And similar to the magnesium there, but the extent is more. However, when there's limited amount of water, okay, then it will just form aluminum hydroxide and release a lot of white fumes, HCl. For these two, they do undergo hydrolysis. They produce white fumes of HCl, which dissolve in excess water to give HCl aqueous, hydrochloric acid. So with limited amount of water, just like your aluminum chloride just now, it forms an oxide. This time around, not hydroxide, oxide, only aluminum form hydroxide and white fumes of HCl. Excess water, it will form aqueous HCl instead. As for PCl3 and PCl5, with excess water and the water is not cold, then you will have H3PO4 and HCl. Okay, when it's just 1:4, which means, okay, you have a lot of water present. The mole ratio of water is much more, right? So you are able to form phosphoric acid. And release HCl. With limited amount of water, where the ratio is 1:1, and the water is cold, okay, you will form POCl3 and HCl white fumes, the gaseous HCl instead. Of course, with more water added, you will form back H3PO4 and HCl aqueous. Okay. Just have to remember the equations very well. Okay, last page, just some conceptual understanding before we move on to the next part on group 2 and group 17. When the salt is dissolved in water, the cations are naturally hydrated by the water molecules due to the formation of ion-dipole interactions. Okay, so as a result, the water molecules coordinate to the cation via the lone pair of electrons on the oxygen. The cations with the high charge density have high polarizing power, is able to distort the electron cloud of the water molecules more easily and weakening the OH bond. As a result, the OH bond will undergo heterolytic fission readily to release the H plus ion. So if let's say let's say for example, aluminium aqua complex, right? So the aluminium, because of its high charge density, okay, this 3+ by the way, is able to distort the electron or to polarize this water molecule. So it pull the oxygen to itself and break this OH bond. So heterolytic fission means both electrons go to O. So the H is removed. But at the same time, the water exert nucleophilic attack. Okay, on the H to remove it. So it forms H3O+, which explains why the aluminum chloride, right, is actually acidic. The stronger the polarizing power of the cation, the greater the extent of hydrolysis. So the more H2O+ will be formed, the pH solution will be lower. For covalent character during hydrolysis, the center atom need to accept the lone pair electrons from water. So in SiCl4, silicon has a low-lying 3d orbital to accept the lone pair electrons from water, as its valence shell correspond to principal quadrant number 3. So this facilitates the hydrolysis reaction. Okay, so you have nucleophile attack, and then you release this, and then plus Cl minus out. So when you form this, and then the water nucleophilic attack again, release this, then you form H2O+. So it should be, I should write this as H3O+, okay, plus Cl minus. So this one come out OHCl. However, CCl4 cannot undergo hydrolysis because for carbon, right, it's very different. The electron division carbon is already attached to 4 large chlorine atoms. It's not like silicon. Silicon has low-lying 3d orbital. Carbon don't have, okay? And since the carbon is really attached to 4 large chlorine, which is because silicon is very large, so chlorine relatively smaller. But for carbon, right, the size of carbon is much smaller. So the chlorine will relatively look bigger. Okay, you know what I mean? So there is actually, for silicon tetrachloride, there's actually less steric hindrance, okay, for the nucleophile to approach. So CCl4, right, it's very hard for the nucleophile to come in because of the hindrance by the chlorine atom, which are relatively large compared to the carbon. So there's another point is a no-lying empty orbital to accept lone pair electrons from water. Since carbon valence shell correspond to principal quadrant number 2, only 4 orbitals, all fully filled. Okay. And that's it for this first part. Let's move on to group 2 elements. This is another long story. Okay. So for group 2, okay. Group 2 metals, right? We just have one lecture just on it, very special. It is known as the alkaline earth metal for 2 reasons. Number one, the oxides from alkaline solution. The oxides form alkaline solution when dissolved in water. That's why they're called alkaline, like calcium oxide, calcium hydroxide. An artifact of history from the predecessors of chemistry. So in ancient times, alchemists attempt to obtain pure metals from ores by heating. They often encountered the group 2 oxides in the furnace. These group 2 oxides melted at such high temperature that they remain as solids. So these solids were referred to as earth. Okay, so they call it earth, that's why it's called alkaline earth. Okay, they have so high melting point, right? They do not just melt. Okay, so these are the characteristics. Their outermost shell configuration is S2, oxidation state +2, and this is the IE trends. Okay, so IE in general, it decreases down group 2 just like group 1. Okay, so for group 2 metals, right, they have a fixed oxidation state of +2. That is because the outermost 2 electrons in the NS shell are easily removed as they are shielded from the nucleus by the inner core electrons. So the two outermost electrons can be easily removed. So they can form +2 oxidation state quite easily. As for +1, also seems possible, given that the second IE is considerably greater, the much higher lattice energy, but then the much higher lattice energy of MX2 compound, okay, will cause MX compounds to disproportionate readily to give MX2 and M. So yes, you may form MX first, all right, but the thing is, it will just, because of the high lattice energy, so it will just break down. Yeah. The enthalpy change of formation of MX2 is actually twice as negative compared to MX. So MX2 actually are more stable, so not likely to be 1+ because of the lattice energy. So the +3 oxidation state, right, is not possible because the third IE is significantly greater than either the first or the second. As the third electron is removed from the inner quadrant shell, this process will require too much energy, which cannot be compensated by the higher lattice energy of MX3 compounds. All right. So let's look at this question. Which statement explains why calcium and chlorine reacts to form calcium chloride instead of calcium CaCl? Let's look at this, pause for a while. Answer should be C. All right, that is energy. Okay, let's look at the physical properties. Atomic and ionic radii will increases down group 2. Okay, both atomic and ionic because of the increased number of quadrant shells. First and second IE decreasing trend in general. Down the group, the atomic radii increases, so the valence electron are further from the nucleus. So down the group, less energy to remove the valence electrons, leading to decrease in first and second IE. That makes sense. Melting and boiling point wise, the melting point of group 2 metals decreases down the group in general. However, there are some irregularity due to the different crystal structure of the metals. So as the size of the cations increases down the group, the attraction between the sea of delocalized electrons and metal cations decreases. So the metallic bonding will weaken down the group. So as you increase the size of cation, the attractions is weakened. Okay. Because the nucleus is further away from the delocalized electrons. Okay, so comparing with group 1s, right? The melting and boiling point of group 1 are significantly, group 2 are higher. Okay, the reason for this is because group 2 have 2 valence electrons, group 1 only have 1. So haven't finished yet. So group 2 also has smaller cation size because across the period the size decreases because greater number of proton, greater effective nuclear charge electrons are more strongly held by the nucleus, resulting in a smaller cation radius. Then group 2 cations have a higher charge density, so more energy to break the stronger metallic bond. Okay. So which factor contribute? It will be the valence electrons lah. Hardness and density. So group 2 metals, right, in fact, are much harder metals when compared to group 1, but softer compared to transition metal. So hardness is related to metallic bond strength and the atomic packing in the metal lattice. So group 2 metals, right, they have 2 valence electrons. The size of the cations is also smaller. So the metallic bond is stronger in group 2. The cations are more closely packed compared to group 1. So it's harder. The density will increase because down the group, the atomic mass increases faster than atomic volume. So overall density increases. So this explain the difference is atomic mass of magnesium higher, atomic radius magnesium lower. So since density equals to atomic mass over atomic radius, so density of magnesium should be higher. Something like that to reason out. And group 2 metals are excellent conductors of heat and electricity. So the mobile valence electron able to transmit thermal energy via rapid translations within the metal lattice. All right, translation means they can move from one end to another very quickly, exciting the lattice by, so when they move, right, they also collide with the cations, and that helps to transmit heat faster by the thermal vibrations of the metal lattice. As for electrical conductivity, because you have this mobile valence electron, they can be charge carriers when the voltage is applied. So these are the data. And resistivity decreases because of increased number of something with the charge density. Yeah. So we can do this at our own time. Chemical properties wise, right, group 2 metals reactivity increases down the group, just like group 1. So the atomic radii increases, the metal atom lose electron more readily down the group. So they form M2 plus more easily. So the metals become better reducing agents going down the group. So the reducing power increases down the group because they are more reactive. You can illustrate this with negative E0 value. So the E0 value become more and more negative, increasing magnitude because of increased reactivity. So likely to get reduced is more likely to be oxidized itself rather. Yeah, so that's why you have an increased negative E0 value. You cannot avoid this. Okay. When group 2 reacts with oxygen, they form a thin oxide layer. Beryllium reacts only when ignited in air. So the reactivity of group 2 metal with oxygen will increase down the group, a consequence of the increase in reducing strength of the metals. Okay, so they do react with water to form oxides, and the reactivity increases as shown by the observation. Very slow, slow, fast, explosive. All right, so this one is actually called barium peroxide. O22 minus is peroxide, by the way. Okay. This one is called superoxide. So just know the difference. Now, so that is group 2 with oxygen increases down the group, which is a consequence of the increasing reducing strength of the metal, meaning they are more easily oxidized. The other one is with water. So it also increases down the group. Okay, so magnesium with water from magnesium oxide, that is with steam lah. Because with water itself is very, very slow. Okay. Then for reaction of calcium with water, can you see that it can actually, it does react with water, but slow reaction. Then you have see that there is a very quick difference. Reactivity increases. Okay, the hydroxide form are not very soluble, but as you go down the group, the solubility increases. Calcium react with small amount of water to form white powdery solid slake lime. In large amount of water, then you form the lime water. So it depends on how much water is added. So this is when you form aqueous, which is lime water, right? It is must be a lot of water. If it's not calcium hydroxide solid, it's called slake lime. With aqueous, it's called lime water. Hydroxide are basically basic, except for beryllium hydroxide, which is amphoteric. All right, that's why it's not listed here. It's also another amphoteric hydroxide other than aluminum, lead, and zinc. Now, so the oxides of group 2, they are white solids, ionic compound, and have high melting point. Okay, except for the amphoteric beryllium oxide. And group 2 metal oxides can be prepared by thermal decomposition of the metal carbonate, except for beryllium oxide. That is an exceptional case. This one decreases because decreasing melting point due to decreasing metallic bond strength due to increasing ionic radius of the cation, which means you bring about let me see, okay, increasing radius, so decreasing charge density. Okay. All the metal oxide react with water to give the corresponding metal hydroxide, except for beryllium oxide. So reaction with water increases with vigor down the group. The resistance of magnesium oxide to hydration by water passivates the metal such that it no further reaction with oxygen or moisture in the atmosphere once the oxide film is formed over the surface. So the magnesium oxide reacts with water form magnesium hydroxide. So this is sparingly soluble to give an alkaline solution. Because of the, why does it not hydrate easily? Because of the oxide layer. For calcium oxide, calcium hydroxide got limited solubility, but it still dissolves. Then strontium oxide is very vigorous, very exothermic. Yeah. Barium oxide also to form barium hydroxide. Very vigorous, so most exothermic. So they react with water to form hydroxide, oxide, water, hydroxide. Okay, remember that. It will be like group 1 actually. Okay, we'll skip this. Because they're all basic. And yeah. Now, let's talk about the thermal stability of the group 2 nitrates, carbonates, and hydroxide. Basically, they are all unstable towards heat, meaning they can be decomposed. So in general, for group 2 nitrates, right, they form oxides, NO2 and O2. Just remember, carbonate, oxides, and carbon dioxide. Hydroxide, oxide, and steam. So, but the similarity is they form oxides, but the difference is the one behind. All right. So the temperature for decompose will also be different. So for group 2 nitrates, carbonates, and hydroxides, right, they become more thermally stable as you go down the group. The one lower down the group had to be heated very strongly before they will decompose. Okay, so why do they become more stable? Because of the polarizing power. So polarizing power refers to the ability of the cation to distort the electron cloud of another ion, atom, or molecule. In general, the higher the charge density, the greater the polarizing power of the cation. So the small, highly charged M2 plus cation in this group 2 compounds that is at the top, the smaller size one, they polarize the anion's larger electron cloud or distort it, weaken the covalent bond within the anion. These compounds, right, decompose on heating as the polarized and weakened covalent bond within the anions are more easily broken. So it weaken this bond, pull this out to form this. So amount of heat is dependent on how highly charged the cation is. The more highly charged, the less heat needed to decompose it, because higher polarizing power of the cation. So for group 2, the cation radius increases down the group. The charge remains the same, so the charge density decreases. So the polarizing power of the cation will decrease and become less able to distort the electron cloud of the anion. Therefore, the ease of decomposition will decrease and hence stability increases down group 2. Therefore, you need higher temperature required to decompose the compound. So with lower polarizing power, the compound is more stable, more difficult to break down. Another factor to look at is from the anion perspective. All right. The polarizability refers to the ease with which the anion, atom, or molecule's electron cloud can be distorted by another ion. So an ion with high polarizing power must have low polarizability, and the converse is also true. So large ions are susceptible to polarization of their electron cloud. Only polyatomic anions are susceptible to decomposition. All right, so only polyatomic ions. So the larger it is, because the larger it is, right, the more easily the electron cloud can be distorted. All right. So the larger the anion, the easier it is to distort the electron cloud and the easier to decompose the compound. So the larger and more atoms per anion, then the more easily electrons can be polarized. More electrons are moving randomly. So they are more susceptible to distortion. The size of the electron cloud of anion inadequately predicts relative thermal stability. Actually, there are other factors like you have to look at like bond strength and arrangement of cations and anions in a lattice, which probably do not feature so critically when one compares different group 2 cations against the same anion. Okay, these factors become more significant. If you, so it's insufficient to just based on electron cloud. It's very superficial actually. Yeah, but it is just at this level will be good enough. So the positive ion can attract the electron cloud of carbonate ion itself. So the carbonate ion becomes polarized with the oxygen atom on the way to become the oxide ion. So it will break down to form the CO2. So this is what happened. This hydrogen carbonate break OH nitrate. The H plus then form OH minus from H2O. So the H plus come out with OH minus from H2O. Here is just NO2, then O, Yeah, with another O to form NO2. So a comparison with group 1 metals, right? The group 1 metal nitrates undergo thermal decomposition, but not to the same extent as the corresponding group 2 compound. The reason for the difference is the lower charge density of the group 1 metal cation. Being larger, cannot polarize the nitrates electron cloud to the same extent as group 2. So group 1 nitrates, right, they will form nitrite, MnO2, and oxygen. That's it. The group 1, they don't form NO2 and O2 like group 2, cannot go so far. Group 1 carbonates are resistant to decomposition, except only for lithium carbonate, because the charge density is high enough because of this low radius to distort the carbonate electron cloud. So it can form lithium oxide and carbon dioxide. The other group 1 metal cations have low charge density because of the large radii and cannot distort the carbonate electron cloud. So the carbonate after lithium do not decompose upon heating. Okay. I'm not going to go through this. You can just check your answer yourself. Okay, so this is just appendix for your own information. I will not go through all this. Yeah. But something interesting here, okay, maybe I go through a bit about beryllium, okay? So beryllium show quite different chemical properties when compared to the rest of the group. In fact, it's actually quite close to aluminium in its chemical properties. So beryllium compounds tend to be covalent. They do not react with water. The oxide also do not react with water. The hydroxide, oxide are amphoteric. They form complexes with the rest of the group does not. Beryllium salts are acidic, but the rest of the group is not. Okay, so beryllium compounds tend to be covalent because of the high charge density. The high polarizing power causes significant distortion of the NRS electron cloud, leading to an overlapping of the cation and anion orbitals. So it forms covalent compound, having high degree of covalency. So compounds which carry large ions like beryllium chloride are actually covalent. Even compounds with small, highly charged anions like beryllium oxide are still covalent. Beryllium, the thing about beryllium is they form impervious oxide layer, just like aluminum oxide. So this layer is resistant to hydration by water molecules, and the metal is protected from reaction. So it does not react with water even when heated red hot, which is a proof to the extremely high stability of the beryllium oxide layer. So they do not react with water, either the element or the oxide itself. Magnesium oxide also forms impervious oxide layer, if you remember, which explains why magnesium oxide doesn't react with water. As for the amphoteric nature, the ionic oxides are basic, but covalent oxides are acidic. So the amphoteric oxide possess both ionic and covalent character. So beryllium oxide, just like our dear aluminum oxide, right? They can react with acid, which means it acts as a base to form salt and water, but it can also act as an acid to react with a base with water to form sodium beryllium hydroxide, aluminate, sorry. Yeah, the beryllinate. So beryllium forms complexes while the rest of group 2 doesn't, like this. The reason why it can do so is because beryllium has 4 valence electrons and it's only 2 coordinate. There's a tendency for it to achieve maximum coordination by acting as a Lewis acid, meaning it accepts electron pair from fluorine to form a complex. Beryllium has a maximum coordination number of 4, and it has only 4 available valence orbital, 2s and the 3 2p. No 2p, so no 6, only can form 4 maximum. This explains why gaseous phase barium chloride is a linear discrete molecule, but in solid state, it consists of a linear polymer. Okay, beryllium cation form a tetrahedral hydrated complex in water. Hydrolysis of the hydrated complex occurs readily in water because of the high charge density. You can pull out one of the OH from here, nucleophilic attack to form the OH. As for the solubility of group 2 salts, it really depends on the solution enthalpy, which depend on both the lattice energy and the hydration energy. Okay, so this is a revision of energetics. So enthalpy of solution equals to minus lattice energy plus enthalpy change of hydration. So in order for salt to be soluble, this enthalpy change of solution must be exothermic. Okay, so we can see that solubility decreases down the group for all the sulfates, carbonates, as well as hydroxides. Okay, more and more insoluble based on the data. So the lattice energy is a measurement of how strongly the ions attract to one another. So in general, ions with high charge density form salts with very exothermic lattice energy. Okay. The magnitude of lattice energy is dependent on the sum of the ionic radii. So the changes in radii affect the lattice energy less significantly than the hydration energy. Yes. That is because you need to sum this up. Hydration energy, right, measures how strongly the ion form interactions with water. So in general, ions with high charge density are very soluble in water, as the hydration energy are very exothermic. So this is the relationship. The magnitude of total hydration energy is dependent on individual ions radii. So changes in radii affect hydration energy more significantly than the lattice energy. So if you look at the trend, the radius, if this one increase much more, then this one will be more positive. So the solution will drop. So the decreasing trend in solubility is due to the increasing radii. Actually, both the lattice energy and hydration energy will decrease. But the hydration energy decrease much faster. This is because the change in cation radii affect the hydration energy more significantly than the lattice. So because of that, if you look at the equation, so this is more, increases more, decreases more. So this one, so your overall enthalpy change of solution is less positive, right? So therefore, changes in the cation radii do not affect the hydration energy as much as the lattice energy. So but the hydration decreases much more slowly. This is because of the small OH size that dominates the value of the hydration energy. Okay, therefore, changes in the cations, small OH minus dominates the value. Therefore, changes in okay, by right, both will decrease, but the decrease of hydration energy is more slowly because the problem is the OH minus size is very small. So the changes in hydration energy is not very big. So therefore, so this one is larger, it's smaller. So overall, the enthalpy change of solution should be more negative, more lattice energy. Yeah, more negative. So increasing negative increasing negative that's for the hydroxide. Hydroxide increases, but the carbonate sulfate decreases because of the, the size of the carbonate and sulfate is much bigger. But for the hydroxide, because it's smaller, they affect less, so more soluble. Okay, that's it. Let's go on to the last one, group 17. The halogens. Okay. The group 17 elements are known as halogens, so I'm not going through this detail. They are most reactive group of non-metals. They are so reactive they cannot exist in nature freely. Then these are the negative ions formed. The last element in the group, astatine, does not occur naturally. In fact, it only have a half-life of 8.3 hours. Yeah, it cannot. So these are the main source of the various halogens. How are they manufactured and their main uses, all right? So they are all diatomic molecules, and these are the electronic configurations. All have Ns2Np5, oxidation state -1, can go all the way to +7, except for fluorine, must die be -1, because it's the most electronegative element. So for halogen to exhibit this variable oxidation state, they must accommodate an expanded octet of more than 8 valence electrons. So for chlorine, bromine, iodine, they are in period 3 onwards, right? They have available 3D, 4D, 5D orbitals to do so, to accommodate 3D here, 4D here, and 5D here. They do have available orbitals from the D orbitals to accommodate the extra electrons. Fluorine, unfortunately, doesn't have. All right, fluorine doesn't have, so it cannot. It can maximum only 8 electrons in the valence shell. Electronegativity, right, as we have learned, is the ability of the atom to attract the shared electrons in the covalent bond. So down the group, the electronegativity decreases. The reason is with increased atomic size, there is increase in shielding effect by greater number of electron shell. So the inner electrons provide more shielding effect. So that will result in a smaller effective nuclear charge. All right, because more shielding effect, the increase in shielding effect overtake the proton number, the nuclear charge. So it leads to a smaller effective nuclear charge. So the shared electrons are attracted less strongly by the nucleus. Covalent radius is half the distance between two covalently bonded atoms in the diatomic molecule. Down the group, the number of covalent shell increases, so the covalent as well as the ionic radii will increase. Bond energy-wise, in general, the energy to break the XX bond will decrease down group 17. Exceptional case will be the FF bond, whose bond strength is lower than expected. Okay, it could be because of the small size, then there'll be some repulsion between electrons to weaken the bond, which explains why the bond energy is rather low. From Cl to I, right, the atomic size increases, so it leads to, why does it decrease from Cl to I is because the orbital overlapping become less effective, because getting bigger, so the bond length become longer, the bonds become weaker. Okay. IE wise, as the atomic size of halogen increases, the valence electron become less tightly bonded. So there are more shielding effect. So effective nuclear charge decreases, IE decreases. Electron affinity that will become less exothermic. Okay, magnitude wise, it got increased a bit here, but then decrease in general. From Cl to I, the number of core electron shell increases. So any electron added to the atom become less strongly attracted. So the ability to accept electron decreases. Okay, electron affinity become less exothermic. F has a less exothermic than Cl because of the extremely small size. Again, we talk about the repulsion between electrons that cause less strongly attraction to the nucleus. Okay, so they are all non-polar diatomic molecules. Dispersion forces between molecules or ID-ID interactions. Going down group 17, the size of electron cloud increases, more polarizable, stronger ID-ID interactions, more energy to overcome, blah, blah, blah. Okay, these are the colors. Pure yellow, yellow-green or greenish-yellow also can, reddish-brown, dark purple, then shiny black, purplish black also accepted. In solution, colorless or light yellow for chlorine, yellow when diluted, orange bromine concentrated, brown for iodine, non-polar solvent, pure yellow, pure green, orange to reddish brown, both are accepted depending on the concentration. Yeah. Pyrite should be yellow, orange for bromine in aqueous state pyrite, violet for iodine. Okay, so the intensity of color increases down the group. As for solubility in water, fluorine oxidizes water to oxygen in a vigorous reaction, even in the cold. Ozone may be formed sometimes, like fluorine with water, form hydrogen fluoride and oxygen. And sometimes it can form ozone, depending. Okay, chlorine will disproportionate. This is the usual reaction. Okay, this one, HOCl itself is a weak acid and will decompose oxygen under sunlight. So this will be the product form. And HOCl is responsible for the bleaching action of chlorine water. So this is the one that bleach. Yeah. Bromine is moderately soluble in water. All right. To form a yellow, orange, yellow-orange solution. It behaves similar to chlorine when in water, but to a smaller extent. Very little HOBr is actually formed. So you have same thing lah. Br2. So Br2 can be, liquid or gas. Also can gas lah. So reversible reaction, it form HBr. You can form this plus HOBr equals. All right. Iodine dissolves very slightly in water. However, it dissolves readily in a solution containing iodide ions to form a brown solution. So this is the brown solution actually. So the iodine, it can actually react with iodide to form a brown solution, I3 minus. It's a complex ion. Halogen being non-polar are more soluble in non-polar. So they exist as free diatomic molecules. So no further reaction like all this lah. I'll skip this. So chemical properties of group 17. So the reactivity will decrease down the group because of increasing EA, harder to gain electrons. Yeah. Increase EA, if you look at the trend earlier on EA, yeah, more difficult because less exothermic. Okay. So okay lah, these are just the variable oxidation state of they can form. Yeah, ICL +1, then +3. This for I. So the I can assume different oxidation state in different compound. The most stable oxidation state of halogen is -1. All halogen except fluorine exhibit positive oxidation state up to +7. Because chlorine, bromine, and iodine can accommodate expanded octet of electrons of more than 8 valence electrons, so they can exhibit variable oxidation state. Fluorine, as I mentioned, do not have available empty d orbital to accommodate the extra electrons. When halogen recombine with metals or non-metals, they act as oxidizing agent. So they can react with metal to form ionic compounds. Fluorine, being the most reactive, combines readily and directly with all metals. Other halogen do not react with unreactive metal like gold, platinum, and silver. Metal, fluorine can. All right. With non-metals, halogen tend to form simple molecular compounds where the halogen is linked by simple covalent bond to other elements. Fluorine reacts directly with all non-metals except nitrogen, helium, neon, and argon. It will even react with diamond and xenon upon reaction. Can form. Even this one can. Chlorine and bromine are much less reactive and will not react directly with any of the noble gases. Carbon, nitrogen, or oxygen. With hydrogen, right? So this is a reaction with metals and non-metals. As for reaction with hydrogen, right? Okay, let's look at the difference. So very explosive in the dark for fluorine. Fluorine explosive under sunlight slow. You can see the reaction rate decreases. The reactivity of halogen decreases down the group, mainly due to the decreasing bond energy, except for fluorine. Okay, don't care about fluorine. Fluorine is always very special. Yeah. The reason for the exceptional reactivity of fluorine is low FF bond strength, high HF bond strength, and very exothermic enthalpy change of formation. So fluorine is very special. Now, oxidizing power of halogen can be measured by the value of the standard reduction potential. So since the E0 value becomes less positive down the group, the oxidizing power will decrease. Okay, so you can actually measure the E0 as we learned in electrochemical cell earlier on. So the halogen can oxidize the halide below it in the group. So the more reactive halogen can displace a less reactive halogen from its halide solution with a positive E0 cell value. So fluorine should be able to displace all of this from solution. The displacement reaction will not take place, does not take place because how come it doesn't? By right, fluorine can based on E0 value, but it doesn't happen because fluorine will react with water instead. Yeah, so reactive, it will react with water. Yeah, as mentioned earlier on, in the earlier reactions, all right? So this one we will just, next time you can just read yourself at own time. Next, chlorine, bromine, and iodine disproportionate readily in alkaline. The products formed depend on the temperature at which the reaction occurs. So when the temperature is cold, low temperature, you have this proportionation. Hot, then you have two steps. So you form chloride. Then this CrO minus will undergo further disproportionation to form Cl minus and ClO3 minus. Then you combine these two, you form this. Same for bromine, very similar, BrO minus, same thing. Yeah. Same for iodine also. Yeah. But as you go down the group, the temperature required will be lower and lower, which means the rate of disproportionation will increase. Yeah, more easily lah. Fluorine, no way. So reaction with Fe2 plus, fluorine, chlorine, bromine can oxidize Fe2 plus to Fe3 plus, but not iodine. Okay, based on the E0 value. So not feasible for iodine. As for S2O32 minus, it can also be oxidized to S4SO4 2 minus. Yeah, it can be done. Sulfate, so thiosulfate become SO4 2 minus. Yep. Iodine also, iodine cannot do SO4 2 minus, only to S4062 minus. So iodine is a weaker oxidizing agent. Yeah. Other properties of hydrogen halide, they are colorless gases. Okay, with contact with moist air, they will form white fumes. So they are all polar molecules lah. Only for HF, very high melting point because of hydrogen bond. The rest is just PD-PD. And PD-PD, then you correspond to electron cloud size lah. All right, okay. Then thermal stability wise, they will decompose, okay, to form the elements. So the bond energy is the highest for HF, so it's difficult to decompose it. Okay, but for HBr, HI, likely more and more. As the atomic radius increases down the group, the bond length will increase, so the bond strength decrease. So the thermal stability will decrease. Yeah, to break down the hydrogen halide. Acid strength will increase down the group law because of decreasing strength of the HS bond. So the weaker the bond, right, the more easily it breaks. The H plus can be released more easily. Yeah, so the extent of dissociation, I mean, more easily break lah. Not say extent of dissociation, but more like more easily break, so more release more easily. So HF is actually a very weak acid, explained by the strength of the HS bond. Then the reaction of hydrogen halide go further. It will react with your silver nitrate, QA. So no PPT, but white PPT soluble. The KSP will decrease lah, more and more insoluble, I would say. Yeah, cream PPT, yellow PPT. Yeah, and so on. So these are the difference. Silver halide are precipitated when aqueous solution of halide are treated with silver ion. The subsequent adding of ammonia result in the formation of stable diamine silver complex. So this is a silver mirror complex. So addition of ammonia will shift equilibrium to the right. So when you add more ammonia, it shift to the right. So this will decrease. So this in turn will shift equilibrium A to the left to increase the solubility of the AgS. So less of the AgS solid. The solubility of the silver halide in ammonia depend on the KSP. So the KSP of the silver halide are considered low and decrease in this order. To be soluble, right, the ionic product must not exceed the KSP. So for AgCl, for example, when dilute ammonia is added, the ionic product of these two will be less than KSP. So AgCl becomes soluble. So when you have less of that, then it becomes soluble. For AgBr, the KSP is even lower. So even at dilute, it still remains insoluble. But you add concentrated, you add a lot of NH3, it will be significantly more to lower the Ag plus, to be lower than KSP. AgI, no hope. As for reaction with lead-2 nitrate, these are the various observations: F minus white PPT, white PPT, white PPT, and yellow PPT. Okay, lead-2 halides are precipitated with aqueous solutions. Are treated, aqueous solution halide treated with Pb2 plus. Okay, so when concentrated sulfuric acid is added to solid halide, the first product is hydrogen halide. Being relatively volatile, right, this hydrogen halide evolved as gas. However, concentrated sulfuric acid is also an oxidizing agent. Okay, so and it's sufficiently strong to oxidize HBr and HI to Br2 and I2 as well. So you have all these halide and product form and the equations. it's just a list of reactions lah, to be familiar with lah. So HS plus acid, NaF, the sodium halide, sulfuric acid HF, just exchange HF, NaHSO4. Then this one has a reaction here, right? NaCl, same thing here. NaBr, HBr, and the HBr can react further with the HBr, HI got a problem. HBr react further H2SO4 form Br2, water, and SO2. Further oxidation. Then same for the iodine. Or this reaction. It depends. All right, okay. This demonstrates the reducing power hydrogen halide B. HI is the most reducing. And go all the way to this. Because it oxidizes. Okay. Lastly, reaction with concentrated sulfuric acid and present on MnO2. MnO2 is a strong oxidizing agent, so you can oxidize HCl to Cl2. You can just read yourself about the reactions. So NaF become HF, same thing. In the HCl, right? So this HCl can be oxidized to Cl2, MaCl2, and water. So the HCl form can be further oxidized by MnO2. Yeah. So from +4 become +2, from -1 becomes 0 lah. It can, yeah, this is the same as just now. Okay, so solid halide with concentrated phosphoric acid also can react. Yeah. You use concentrated phosphoric acid to oxidize it. Sorry, to react with it to form your from the solid halide to the hydrogen halide. So this is in general. Okay, that's it. Hope you enjoy this session.